Hello, welcome to the IMS pre-conference tutorial. My name is Daniela Kabrek and I will present new spectrum access paradigms, in particular related to radar communications coexistence and millimeter wave spectrum sharing. Here is the outline of my talk. I will first introduce Spectrum X, which is the NSF-funded Center for Spectrum Innovation. And then I will provide a background on several research activities and considerations of spectrum coexistence use cases. And then I will focus on two specific use cases where we conduct research on radar communications coexistence and millimeter wave spectrum sharing. I will provide a summary and directions for future research. NSF funded Spectrum X, which is a center for spectrum innovations, in 2021 with the objective to provide research platform for innovations and effectively transformation of the landscape for spectrum access and management. The center is led by University of Notre Dame, and there are several research universities as well as industry partners. And the vision is to, as I said, change the way the spectrum is managed from a highly regulated, licensed, unlicensed, permit-based to fully flexible, dynamic, data-driven, and automated framework. What that means is that the boundaries and mechanisms how the spectrum is accessed across broadband, defense, as well as many scientific uses, for example, radio astronomy and weather sensing, can be coordinated in very new and creative ways, some of the examples being overlaid spectrum access, incentive auctions, and so forth. At the same time, the idea is also to provide a much better understanding of spectrum usage through spectrum sensing and deploying actually very large scale sensor infrastructure that will be feeding the cloud with the data and providing regulators, being FCC and NTIA, about the opportunities for spectrum sharing and better coordination of spectrum access. The project teams are organized into 6 trusts. There is a trust on coexistence with passive scientific receivers, including weather and astronomy. There is also a trust on active coexistence, where there are many examples, including cellular, radars, satellites, and so forth. And I'm the lead of that project. And today we will hear more about some of the project activities. There is also trust on sensing, including the low-cost sensor design and system deployment for spectrum monitoring. There is also a project on that kind of relates to both sensing and also active and passive coexistence, which is kind of understanding these multidimensional measurements taken by the sensors and providing real-time spectrum awareness. There is also angle on economics and policy through rights and trying to understand what are the new flexible ways of providing access. And lastly, there is a project on enforcement, and that is to understand how the both primary, secondary, and all users within the spectrum are ensuring that they have access rights and also security. The spectrum is a finite resource, and over time, the demand for spectrum has been increasing, in particular due to the development of cellular technologies, but also satellites and advancement of DoD applications. So the FCC has been continuously evolving with its models for spectrum assignments and also models for sharing. And we see that over time, this evolution was actually driven by lots of demand, but also conflicts. And it is indeed very challenging decision, both from economics, policy, and technology point of view. How are the bands, especially in the kind of prime real estate of lower frequency bands, going to be assigned? At the same time, moving to higher frequency bands has created kind of new challenges, because lots of bands are allocated to atmospheric science and weather in the upper kind of going into millimeter wave spectrum, as well as for the radio astronomy. So this was actually one of the main motivations for the center to take a very comprehensive understanding, analysis, and also come up with some creative ways of informing FCC and NTIA about spectrum in the future. So from the active coexistence point of view, most of the bands, if not all, are actually dealing with sharing or coexistence of cellular kind of communications and other potentially incumbents in the band. And this is particularly important in light of developing 5G and also looking ahead in 6G. So traditionally, the bands that have been used for cellular are below 7 gigahertz, and this band is now referred to as FR1. However, most of the frequencies in this spectrum have been already allocated. In recent years, in like 2017, FCC has released licensed bands in millimeter wave spectrum, which is the FR2, and 5G has kind of took that opportunity and developed cellular solutions for millimeter wave band. However, due to the propagation characteristics of these frequencies, there is also kind of a need to move in bands that, again, have better coverage. So the new opportunity is this upper mid band between 7 and 24 gigahertz, also referred as FR3, and in the kind of broader industry as well as FCC kind of discussions, this is potentially a spectrum for 5G advanced and 6G. However, this band actually brings lots of new challenges and ways of finding how to coexist with other services, as I mentioned, satellites, radio astronomy, and radars. Within the spectrum active coexistence projects, we are investigating sort of 3 approaches to enable active coexistence. First one is based on measurements, effectively advanced spectrum sensing for interference management. And in particular, this approach is relevant for one of the bands that has been already shared between the cellular and radars, which is CBRS, and it is from 3.55 to 3.7 gigahertz. And this approach is kind of in contrast to currently managed centralized database approach to distributed coordination mechanisms and measurement informed interference. The second thrust is related to exploiting abundant degrees of freedom and also coordination between radios. So what does that really mean is coexistence, active coexistence, and as we will discuss more in this tutorial, can be actually very effectively managed through, for example, antennas, having large antenna arrays, in particular at our base stations or radars, as well as much wider frequency resources. So today actually we'll spend time discussing radar and communications coexistence, as well as millimeter wave spectrum sharing, where both wideband characteristics as well as large antenna arrays are providing opportunity for coordinated and also interference management. And lastly, advancements of machine learning have shown lots of potentials in other fields. And in our active coexistence projects, we're also looking into how these tools can be used to do interference management or interference awareness, estimation, and better guide sharing of active transmitters. Now let's start with the first use case where we will consider the radar communications coexistence scenario. So this would be an example in, let's say, 3.1 to 3.4 gigahertz band, where we have a radar for kind of airborne type of traffic monitoring. And this radar is in the geographic area with several, let's say, 5G base stations. And the goal would be to enable effectively coexistence in the same frequency band between these two disparate wireless communication. Actually, wireless communication, and another one is a sensing system, because it is a radar used for tracking and localization of targets. Modern radars are typically equipped with antenna arrays. And with the technology advancement, these radars are becoming larger to provide higher gain, meaning longer distance tracking, as well as good resolution. However, there are lots of challenges in processing these radar signals due to high bandwidth, and also real-time operation due to the short pulse repetition interval, and so forth. Now, these radars, in addition to just target tracking, basically need to provide robustness to resilience to interferers or undesired sources in the band. And the problem is that this also introduces kind of computational complexity. And the goal is really to provide radars with a lower complexity and adaptive solutions that can potentially be programmable in a sense that they can be added to existing radar hardware, while at the same time ensuring high resolution and also awareness of where the interference is and target tracking. And the goal is also to make it scalable for large arrays. So this was indeed also kind of studied in the context of DARPA program, Triad, which was short-term, like an 18-month project to demonstrate advanced array processing on large-scale digital phase arrays, and also use both machine learning as well as tensor operations to provide kind of fully adaptive beamforming capabilities for radars. So I was on the team actually with Raytheon and NVIDIA, and we have developed both algorithms as well as kind of GPU acceleration, and demonstrated that radars indeed are capable of suppressing the interference solely due to actually large number of antenna elements and having a digital antenna array. Well, this use case was related to kind of radar protecting the interference. One can envision that also base stations equipped with hundreds or so antennas will also have this capability of interference mitigation as well as adaptive beamforming. So in this project, we have considered the digital array radar and used several algorithms, both based on machine learning as well as kind of classical signal processing to enable three things. First, the radar array was able in real time to estimate with a high resolution angles of arrivals for all interference sources. And this approach was based on deep learning assisted signal processing. So I'll talk more about this. And then based on this information of interference directions, we developed a solution for very fast, computationally efficient beamforming design, and that can actually suppress very large number of interference sources. The solution is fast because it avoids actually complex matrix inversions and operations. Now, in the radar setting, the number of beamformers, especially because of tracking one or multiple targets, the number of beamforming coefficients needs to be computed very fast, and also very large number, let's say on the order of 1,000 beamformers for search and scan. And for that, we have also provided some machine learning or reinforcement learning assistance to kind of guide the radar to kind of focus on only relevant direction, and also be robust with respect to the interference. The first step in our algorithmic framework was to reliably and with a very high accuracy estimate the angle of arrival of multiple interference. However, due to the very large size of the array and also very large number of samples per every IQ channel, there is a prohibitive complexity both in terms of computation as well as the kind of effective throughput of these IQ samples. So our approach was based on sparse signal processing, where in the first step we would apply very coarse discrete Fourier transform in a spatial domain across angle, azimuth, and elevation, and then rely on trained neural network, convolutional neural network, for interpolating these spectrum to a very fine resolution, as well as predicting how many interference sources are there for nulling. And this approach was indeed tested using that array hardware in the field, and compared with much higher complexity solutions based on signal processing, such as 512 by 512 discrete Fourier transform, which indeed was used as a ground truth. And in this case, we had two interference sources. Similarly complex music algorithms are also able to find these with a very high resolution. However, these solutions are not real time, which is indeed one of the key requirements for agile kind of and responsive spectrum access. And our solution, as I said, started with a 16 by 16 DFT, and then used these interpolator neural networks, and again with the high accuracy compared to similar accuracy to DFT and music, was able to localize these sources. The next step after identifying the interference sources is to adapt the beamforming and effectively reject or suppress the interference. So state-of-the-art methods, which are from the signal processing perspective, these minimum variance distortion ratio beamformers are prohibitively complex. Why are they complex? Is because they rely on basically computation of n by n matrix, where n is the number of antenna elements in the array, and then inversion of that matrix. So this actually kind of computes these W coefficients, which are kind of per element weights, but the order of complexity is n cubed. And therefore, we had to resort to lower complexity solutions. So one of the approaches that we studied is, if we already estimate the angles of arrival for this interference, being psi j, we can actually, based on these parameter estimation, compute the covariance matrix in a low complexity way, meaning that we don't directly use IQ samples, but rather use angle estimates, and then perform these matrix inversion because the matrix has a structure, and then reduce the complexity that scales with the number of interference sources cube. So this is indeed a very promising solution that we were immediately testing on the actual array. Now, one of the problems that one has to be careful in kind of relying on estimates as well as kind of constructing the beamformers is that there are lots of practical design considerations, most importantly, calibration of the array. So indeed, the physical array had both amplitude and phase errors that we didn't take into account in our algorithm design. And as a result, there is actually a huge difference between the method, this first method, which is inversion of that sample covariance matrix, indeed is robust to the calibration errors. But as I mentioned, it has that n cube complexity. So this was our reference. And here what we look at is if you were to measure the residual interference in any of the directions, if you're pointing the beam in any of the directions, here is the azimuth and elevation map, basically the level of interference that you would get is kind of denoted by darker colors. The only places where we cannot provide any interference suppression are the red dots, and that's actually where the interferers are. Now, our proposed solution, where we estimated the positions of the interference and constructed the beamformer, effectively provided much shallower null depth. There is about 15 dB degradation between the two. And we have studied also via simulation kind of the impact of these phase and gain errors on the null depth. And again, characterize that, as we see here, the worst case beam patterns have very bad, actually, nulling performance. So this is indeed a big lesson learned that we had to take into account and kind of improve upon our adaptive beamformers for the interference suppression. We have also demonstrated this robust beamforming with FISTA using our Raytheon large-scale over 100-element array. So here is kind of a real-time scan across azimuth and range, and the yellow stripe actually corresponds to the strong jammer along these directions. So as we can see from this movie, the FISTA beamforming is effectively removing or nulling that direction. And if you look at kind of as a function of coordinates, we were able to actually detect the aircraft. The yellow colors on the bottom are indeed due to clutter. We have also compared the interference suppression for all three methods, and the reference was actually the most computationally expensive solution, which is this SMI-MVDR. And kind of this is theoretically the best we can do in terms of suppression for a given array. And the difference between the conjugate gradient and SMI-MVDR is within the 0.2 dB suppression with only 10 iterations. So indeed, this was the winner algorithm in our case. FISTA is indeed providing within 3 dB suppression from the optimal objective and requires 25 iterations. And we see that the first approach where we try to first estimate the directions and then kind of reconstruct the both beamformers and reduce the complexity indeed remained very inferior. There was that 15 dB worst case residual interference that we couldn't suppress. So with respect to radar and communications coexistence, we have provided particularly important and I think promising insight that digital arrays, both on the radar side as well as, I would say, on the base station side, provide large number of degrees of freedom so that one can estimate the interference directions with high accuracy, and also provide very robust suppression of interference. And this was also successfully demonstrated in real measurement data. For more details, I would refer you to the paper that was recently published on transactions on radar systems. In the next section, we will look at actually a different problem. We will look at now spectrum sharing in cellular bands. And indeed, this is now a coexistence within, let's say, operators, different operators, operator 1 and 2, that are currently actually being allocated different frequency bands. And as a result, lots of spectrum is actually wasted and not used because operators are effectively not coordinated. So the idea is that both operators can actually use both bands, meaning that they can share it based on the deployment, but they need to find a way to manage the interference. So this is actually one of the propositions that the spectrum sharing between operators can be also a new way of improving the spectrum utilization. So again, our solutions are relying on multiple antennas. And this is kind of not just because we want to use it. Indeed, for a fact, at least in millimeter wave bands, we have base stations and mobiles with lots of antennas. And also the trend is even in sub-6 and in this upper mid-band that multiple antennas will be a solution. Now, in contrast to our radar kind of approaches, here we are looking into lower complexity solutions because of kind of digital arrays potentially being too expensive for both mobiles as well as the base stations. So we will discuss a new radio architecture, antenna array architecture based on true time delay that actually has a lot more flexibility compared to phased arrays and allow us to do not just beamforming, but as I also alluded, we would like to do interference management, which would require placement of nulls. So the true time delay array is indeed an analog array, has only one RF chain, but in addition to phase shifters, it has a delay element per antenna. So in this scenario, we're looking at a receiver that is trying to protect and basically improve its signal to interference and noise ratio by having, let's say, a desired signal and then multiple interference. And the objective is indeed to have, again, good estimate of directions of arrival for both desired and also interferers. So this would be kind of for the purpose of optimizing that beamforming gain. But at the same time, we would like to also design the true time delay phases and delays to steer the nulls towards the interferers without hurting the desired signal. So what is interesting and nice, and my group has been working a lot about true time delays, that not only did they have these wideband beamforming capabilities, meaning that their response is kind of same across all frequencies, but they also provide a structured way of designing beamformers. So we actually have a very elegant solution for creating a beamforming coefficients for a given set of directions. So if we know, for example, direction of desired signal and then directions, not only one, but multiple interferers, we can actually create a wideband null and also maximize the beamforming gain. And the solution actually relies on a very kind of mathematical way of designing these beamforming coefficients through a Kronecker decomposition. So effectively, we will look at our antenna array as kind of a nested spatial filtering problem. So indeed, this Kronecker decomposition says that any kind of beamformer can be decomposed into a subset of beamformers. In this case, we're saying this is just an example of W3, W2, and W1. And indeed, these beamformers are, as I mentioned, nested. So there is actually a kind of a sparsity in the array because these elements are spaced by number of antennas, and then D1 and D2, which is kind of how many partitions we have. And each of these spatial filters is actually controlled by delta tau and delta phi, which are kind of proxies for designing delays and phases of our TTD. So, so this is effectively, as I said, multi-stage frequency spatial filter. So now, if we take n element antenna array, we can actually divide this into k, which is log 2n spatial filters of size 2. So, and each of these spatial filters actually is now controlled by taus and phis, and there are k of them. So now, the way we actually create our phases and delays is by performing this mathematical operation of Kroneker's, so that we can actually get delays per element. So this is for the case of 8 elements, we actually can mathematically compute this. But we did see that we only have, for 8 elements, 3 degrees of freedom because our k is log 2 of 8, which is 3. And now what is interesting is, because these are spatial filters, each of these terms can be used either for nulling or kind of getting a gain in a particular direction. So if we want to null the interferer, we would set this tau tilde to be basically dependent on the direction of the interferer. And then indeed the phase term of pi would provide the nulling. On the other hand, phase term of 0 would provide a gain in the desired direction. So indeed, this Kronecker decomposition is a very fast way of placing wideband nulls. In this case, we see that across a very wide frequency band, we have nulling, which would not be possible actually with phased antenna array alone. Now, what is kind of interesting about these Kroneckers is that, fine, we can do placement of the nulls by kind of selecting taus and phis, whether we want to beamform in that direction or null. However, we see that we actually have multiple terms, and it's not really obvious which term should be used for nulling versus interfere. So indeed, there is dependence on choices of nulling factors. So for this case that I showed you, which is 8 antenna arrays and 3 Kronecker terms, we indeed have 6 possible combinations which term to choose for which interfere. Okay, so we can actually, I mean, we technically choose 2 and the third one is determined. So if we're kind of deciding for the terms for the interferers, so let's say P is for interferer 1 and Q is for the interference 2, then we can have a third term for interference 1 and let's say first for interference 2 and all possible combinations. So what we see is that the beamforming responses as a function of desired angle will change drastically. And keep in mind that we also have a desired angle to satisfy. So what is actually important is that we need to optimize our Kronecker choice and come up with the best region. So now, indeed, there is an algorithm to determine optimal nulling combination. And that is, out of all these combinations that you have, you would pick the one that is giving you the highest gain in the desired direction, while the nulls are guaranteed due to the Kronecker. So indeed, we have kind of limitation in terms of how close we can have desired signal and the interferers. So indeed, even with this optimization, we will have a blackout region, which is if the, let's say, antenna array with 8 elements, if the beamforming gain drops below, let's say, 3 dB or half in linear scale, we won't be able to serve the user next to that interfere. Now, this is kind of, that blackout region is effectively related to where the interferers are. This is just an example of 2 specific positions of the interferers, but in general, there is actually, blackout region within 17% is indeed for an array of size 8, not very bad. But one thing that we also studied is that it can be improved with larger arrays. So indeed, this blackout probability for 8 by 1 array is can be improved by adding more. So with 32 elements, the blackout probability can be a couple of percent. Now, this approach for fast, basically interference nulling and kind of enabling coexistence of multiple cellular kind of operators in the same band also requires estimation of these directions. Because if you remember, I have assumed that the directions of both desired signal and interference are known. Now, we have also kind of showed that the true time delay arrays have this capability of fast estimation because they can create these dispersive beams and effectively scan all directions at once. Now, the problem is that even though they are sensing all directions at once, meaning that they can quickly they avoid a sweep which will be the phase antenna array approach. The problem is we only have one measurement because we have one RF chain. And that is the reason we introduced this idea of separate pilots for the desired and interference signals, so that indeed, let's say one cellular provider would have its own specific pilots that will allow to distinguish what are the directions of the desired signal, and then the other ones would be interferers. So we have developed this algorithm that can estimate, because of this pilot separation, both desired angle of arrival as well as interference. And we have also studied this approach and also compared it with digital arrays, because indeed one of the candidates for cellular in upper mid-band as well as millimeter wave band is a digital array. However, our objective was to kind of find whether lower cost and also lower energy consumption solutions such as true time delay are competitive candidates. And here we see that with respect to estimating the angles based on how strong the interference is, for example, 20 or 20 dB above the noise or 0 dB, we have a very high accuracy of the interference estimation. And we have also studied how much we improve or like how do we compare in terms of spectral efficiency compared to the fully digital arrays. So the yellow lines are showing what would be the spectral efficiency of a fully digital, and then green and blue are showing the true time delay. And again, we see that as we increase the array size as expected, the spectral efficiency would improve, which indeed shows that the coexistence of multiple operators in the same band is feasible. There are more details in this paper that is actually recently accepted and will be presented at IEEE DISPAN in May of 2024. So in summary, I just gave you actually a short overview of what are the exciting kind of spectrum access and management projects that we're pursuing in the center. I have mostly focused on active coexistence, which and within that, two use cases. One is the coexistence with DoD incumbents, such as radars. And although I looked at from the radar perspective, there is also kind of equivalent kind of argument for base station protecting the radars through interference nulling, and also spectrum sharing across cellular operators with some interference consideration. The key tools, I believe, are using antennas, not only for improving the spectrum efficiency and beamforming gain, but thinking more creatively about interference nulling, which also would appear in coexistence with satellites, and then also radio astronomy. And we're also learning how machine learning can help us facilitate robustness and also improve the speed of our algorithms and convergence. Thank you so much for your attention.